Alright, so we're going to have a look at another question. This is an ordinary differential equation. So far we've seen first order differential equations which are separable with and without initial value conditions, first order differential equations which can be solved with integrating factor with or without initial conditions. Now we're going to have a look at some second order differential equations. So the question we have here, and this one will be with initial conditions. So we're going to have a look at y double prime plus 2y prime plus 5y is equal to 0. So this is a relatively simple form. This is a second order differential equation. The highest derivative is a second derivative. This could also be written as, if we wished to write this in the Leibniz form, we could write d squared y dx squared plus 2 times dy dx plus 5y is equal to 0. So these are completely equivalent. Either form will do here. In fact, the note set that these questions come from uses the y prime form, but it really doesn't matter. But they're both the same. So we're going to solve this, and we are given two initial conditions, one for the function, one for the derivative. So we are told that y of 0 is equal to 2, y when evaluated at 0 is equal to 2, and we are told y prime of 0 is equal to 0. Prime of 0 is equal to 0. So first we need to work out what the solution is. So first we need to find our general solution. So we have y double prime plus 2y prime plus 5y is equal to 0. Well, this is a second order differential equation. So the coefficients will form a characteristic polynomial. So a is 1, b is 2, c is 5. So this will give us the polynomial x squared plus 2x plus 5 equals 0. Now we need to find the roots of this. If it has two distinct roots, this differential equation will have one known solution. If it has a double repeated root, it will have a different solution. If it has complex roots, it will have a different solution again. So we're just going to solve this quadratic equation. So we could try and factorize this. This looks like it's two numbers that multiply to make 5, add to make 2. It doesn't look like that's going to work very nicely, so we'll use quadratic formula. So we have roots 1 and 2 are minus b plus minus the square root of b squared minus 4ac all over 2a. So we get minus 2 plus minus the square root of 4 minus 4 times 1 times 5. So 4 times 5 is 20, that's minus 20. This is all over 2 times a, which is 2. This gives us minus 2 plus minus the square root of minus 16 all over 2. So the square root of minus 16 is actually the square root of 16 times the square root of 1. Square root of 16 is 4. So this becomes minus 2 plus minus 4i over 2. And then we can divide everything by 2. We'll get minus 1 plus minus 2i. So this is two complex roots, right? This is not real roots. It's not repeated real roots. It's two distinct complex roots. And so we know in the case where a second order differential equation of this form, in the case where the characteristic polynomial, this is the characteristic polynomial, in the case where this characteristic polynomial has two imaginary roots, we can find the solution using the following formula. So we have y of x is equal to c times e to the x times cosine. So we want a general form for these before we plug it in. So let me be a little careful with how I'm writing this. The specific form that we would like is c times e to the alpha x times cosine of beta x plus d e to the alpha x times sine of beta x. So this is our specific form, and we're going to get the alpha and the beta from the complex conjugate pairs. So in this equation we had minus I plus minus 2i. Well, the real number we're going to be calling alpha, and then the coefficient of the complex number we're going to be calling beta. So in this case alpha is minus 1 and beta is 2. So this means our general solution will be y of x is equal to c times e to the minus x times cosine of 2x plus d times e to the minus x times sine of 2x. So this is our general solution. Notice this has two unknowns in it. It has a c and a d, but this is the correct general solution. Now we're going to use this general solution and these initial conditions over here in order to find a specific solution. So we actually first need to differentiate this because we have a y0 evaluation here and a y prime evaluation here. We only have a y of x here, so we need to differentiate this to get a y prime, then evaluate them both simultaneously. They'll be functions of c and d. We can solve for c and d using simultaneous equations, essentially. So if this is our function, we are going to have two product rules. So the first one, u will be c e to the minus x, u prime will be minus c e to the minus x, v will be cosine 2x, v prime will be, cosine becomes minus sine, minus 2 sine 2x. So this is the derivative just of the first part. We're not even up to the second part yet. And then the second part's derivative, so these are all u1, u1 prime, v1, v1 prime. Then we'll have u2 is de to the minus x. u2 prime will be minus de to the minus x. v2 will be sine of 2x, and then v2 prime will be cosine, 2 times cosine of 2x. And so now we need to do the two product rules, compose them together, add these two product rules together. This will give us the derivative. So this implies y prime of x is equal to u prime v plus uv prime. So that's minus c e to the minus x times cosine 2x plus c e to the minus x times minus 2 sine of 2x. So this is minus 2 c e to the minus x times sine of 2x plus the second product rule. So this will be plus u2 prime times v2 plus u2 times v2 prime. So this will be not a plus here, it'll actually be a minus de to the minus x sine of 2x, and then a plus de to the minus x times 2 times cosine of 2x. And this is our first derivative. Now, one thing we want to try and do straight away is we want to try and factorize this if we can. A lot of stuff does have e to the minus x in it. A lot of stuff does have sine and cosine. So you'll notice we could factor e to the minus x times cosine out of two of these terms, this one and this one, then do the same for sine. We could do sine first, actually, because that would give us sine first, which makes sense. It doesn't matter the way in which we do it, but we'll do sine first. So we have minus 2c e to the minus x sine of 2x here. So we can take e to the minus x sine 2x out the front. This is going to be multiplied by minus 2c minus d. So that's these two sine terms. And then we have e to the minus x plus e to the minus x times cosine of 2x. This is going to be multiplied by minus c, which is the first one, plus 2d, which is the second one. And this is a factorized form. It could be factorized even more. We could take e to the minus x out the front, and this would give us sine of 2x times minus 2c minus d plus cosine of 2x times minus c plus 2d. This would give us something like this. This is not necessarily any better in this case. They're similar forms of the solution. So, but both of these are a little bit neater than the one we started with. So these are preferable first derivatives. So now we know the solution, the general solution. So this is our general solution. We know the general solution's first derivative. General solution's first derivative. And now we can plug all the values into these. So we have y of 0 equals 2. That means y is 2 when x is 0. And we have y prime of 0 equals 0. That means y prime is 0 when x is 0. So we know when x is 0, y is 2 and y prime is 0. That's what this is telling us. Both of these are actually when x is 0. So we'll use the general solution. So y of x, so for our gen solution, plugging this in, when x is 0, we will have y of 0, which is 2. 2 is equal to c times e to the minus 0 times cosine of 2 times 0 times cosine of 0 plus d times e to the 0 times sine of 0 plus d times e to the minus 0 times sine of 0. Now, conveniently, e to the 0's just become 1s. Cosine of 0 is 1. Sine of 0 is actually 0. So this tells us that c has to be equal to 2 times 1, which is 2. So now we know what c is. So we used our general solution, plugged in the information we were given. This gave us the c. Now the harder work begins. Now we have to do it for this first derivative. So the first derivative here, we've got to plug in y prime equals 0, x equals 0. So now the gen solution's first derivative evaluation is going to be y prime of 0, which is 0, is equal to, I'll use the second one because I can keep it on my screen here, e to the minus x, so that is e to the minus 0, times sine of 0, times minus 2 times c minus d. Well, we know c is 2, so minus 2 times 2 is minus 4 minus d. Then plus cosine of 0 times minus c plus 2d. Well, we know c is 2, so that's minus 2 plus 2d. It's 2d. So we have this equation. Now from this, we should be able to get d. Cosine of 0 we know is 1. Sine of 0 we know is 0. So this actually goes away. E to the 0 we know is 1. So this gives us 0 is equal to, the only thing remaining is minus 2 plus 2d. So we have minus 2 plus 2d. This tells us that d is equal to 1. So in fact, c equals 2, and d equals 1. Now, This means that our specific solution is going to be y of x is equal to 2e to the minus x times cosine of 2x plus 1 e to the minus x times sine of 2x. And so this is our specific solution. So this is what we were after. As is typical of these questions, we're not actually finished at this point. We now have the specific solution. We can differentiate it, and then we can differentiate it again and find the first derivative and the second derivative, and we can plug them in to the question to prove that this is a solution, and you better believe that we're going to be doing this. This question obviously is a little long, has a lot of working in it, but you know, this is good practice, right? You should be checking that these are right. And we can do this, even though it is somewhat annoying to do. We can do this. So we have our specific solution here. Now we want to take the derivative. So we're going to need to do two product rules. So again, we have u1 is 2e to the minus x. u1 prime is minus 2e to the minus x. v is cosine of 2x. v1 is cosine of 2x. v1 prime is minus 2 sine of 2x. And then our second product rule, u2 will be equal to e to the minus x. u2 prime will be minus e to the minus x. v2 will be sine of 2x. v2 prime will be equal to 2 cosine 2x. And then we're just going to do product rules. So u prime v plus uv prime, u prime v plus uv prime. So this tells us that our first derivative, y prime of x, is u prime v minus 2e to the minus x times cosine of 2x plus uv prime, 2e to the minus x times minus 2 sine of 2x. This will actually be minus 4 out the front. Minus 4e to the minus x sine 2x plus u2 prime times v2. So this will be minus e to the minus x times sine of 2x plus u2 times v2 prime, which will be plus 2e to the minus x times cosine of 2x. Now we can group these together. This will give us y prime of x is equal to, well, we have, what do we have? We have minus 2e to the x cosine 2x plus 2e to the x cosine 2x. So these, and we want to be very careful to make sure these actually do cancel. If they're going to cancel out, that's very convenient. This looks like it's going to cancel with this. And then we have minus 4 e to the minus x sine minus 1 e to the minus x sine. That's minus 5 e to the minus x sine of 2x. And so this looks like it is our first derivative. So this is the function. And then this is the first derivative. But we need the second derivative to actually prove this. So now we're going to do, better believe it, more product rules. So u is minus 5 e to the minus x. U prime is 5 e to the minus x. V is sine of 2x. And v prime is 2 cosine of 2x. So now we have u prime v plus uv prime. So this tells us y double prime of x is equal to 5e to the minus x times sine of 2x minus u times v prime. It's a minus because of the minus here. It's plus, but it becomes negative. This becomes 10 e to the minus x cosine of 2x. And this is simplified. This is our second derivative. So this is our function up here. These are our two derivatives. Now we have to plug everything in. So we'll do this over on this side. So we have y double prime plus 2y prime plus 5y equals 0. So this means that 5 e to the minus x sine 2x minus 10 e to the minus x cosine 2x plus 2 times minus 5 e to the minus x sine 2x plus 5 times 2e to the minus x cosine 2x plus e to the minus x sine 2x is all equal to 0, apparently. So now we're going to expand everything and see if this is true. So we have a 5e to the minus x sine 2x up the top minus 10 e to the minus x cosine 2x. Then we have 2 times minus 5, so this becomes minus 10 e to the minus x times sine 2x. And then down the bottom we have 5 times 2, so this becomes plus 10 e to the minus x cosine 2x plus 5 e to the minus x sine 2x is allegedly all 0. Well, now we can just cancel. So we have a plus 10 e to the minus x cosine, and we have a minus 10, so they cancel. We have 2 plus 5 e to the minus x sines and a minus 10, so this all cancels. So this definitely is 0. So this definitely, the function that we have over here on the right hand side of the screen, this thing, this definitely is a possible solution to this second order differential equation. And this was one way to do this.